Newton's comprehension of gravity was sufficient to enable us to journey from the Earth to the Moon. Have you ever found yourself disoriented in the relentless march of time, pondering whether our grasp of it is merely the surface of a vast temporal iceberg? At its core, his insight is not just a hypothesis. It's a key that could unlock the enigmas of the universe, unveiling a cosmos more complex and awe-inspiring than we ever dared to conceive. How does Brian Cox's recent hypothesis challenge our conventional perception of time, and what could the potential ramifications be for our understanding of reality? Join us on a fascinating journey through the corridors of time itself as we explore Brian Cox's recently disclosed groundbreaking theory regarding the essence of time in the immense universe surrounding us. Mysteries await discovery, and some of these puzzles pertain to intriguing aspects of time and gravity, which are vital components of our existence. Imagine a reality where time behaves oddly. It can either decelerate or accelerate. Furthermore, the force that keeps us anchored to the ground might not be as it appears. This is the domain of Albert Einstein's theories of relativity, where our comprehension of time and gravity takes an unusual twist. Albert Einstein, a renowned figure, provided us with a novel perspective on the cosmos through his theories of relativity. His work established the groundwork for understanding how time functions in various circumstances, particularly when moving at extraordinarily high velocities. It all commenced in the early 20th century when Einstein proposed two revolutionary theories: the special theory of relativity and the general theory of relativity. The special theory of relativity, released in 1905, transformed our understanding of time and space. In straightforward terms, it asserts that the principles of physics remain consistent for all observers who are not accelerating, regardless of their motion. This theory introduces the concept of relativistic effects, including the well-known idea that time can dilate or slow down under specific conditions. One captivating thought experiment used to illustrate time dilation is the light clock. Picture being inside a spacecraft moving incredibly fast, nearly at the speed of light. Within the spacecraft, a beam of light bounces between two mirrors that are perpendicular to the direction of movement. According to the laws of physics, the speed of light is invariant for all observers, meaning the light beam must appear to traverse a longer diagonal path. The duration it takes for the light beam to cover its route should be identical for both the observer inside the spacecraft and the one outside. However, since the path is lengthier for the outside observer, it appears that it would require more time for the light to complete its journey. This perceived time discrepancy between the two observers is what Einstein termed time dilation. Time decelerates for the moving observer relative to the stationary observer. In this situation, time behaves differently based on your motion. Grasping how phenomena alter when they move rapidly, known as relativistic effects, is not merely a theoretical concept. Scientists utilize large machines known as particle accelerators like the Large Hadron Collider to propel particles at incredibly high speeds, nearly as fast as light. When entities move at such velocities, we must conceptualize time in a unique manner to make precise predictions and measurements. Albert Einstein formulated the special theory of relativity in 1905, and it revolutionized our perspective on the universe, particularly regarding time and movement. This theory challenges our instinctive notions. It posits that the laws of physics are consistent for everyone, even if they are stationary. This contrasts with our daily experiences, where we might believe that if something is already in motion and we add more speed, it accelerates further. However, Einstein's theory states that there is a maximum velocity that nothing can surpass, and that is the speed of light. In this way of thinking, events that appear to occur simultaneously for us might not seem that way for individuals moving nearly as fast as light. Another idea emerging from this distinctive viewpoint is length contraction. This implies that if an object is in motion, it appears shorter in the direction of its movement when observed from a stationary location. Then there's the renowned equation E = mc²2 which illustrates that energy and mass can convert into one another. This is significant for comprehending how minute particles behave when they are moving at high speeds, as well as for phenomena like nuclear reactions when atoms split. In reality, special relativity is not just an elaborate theory. It plays a role in everyday technologies like GPS. When GPS satellites transmit signals to your device, they are in motion, and because of this movement, time behaves somewhat differently for them. If we failed to consider this time dilation effect in our GPS computations, your navigation could be significantly inaccurate. Thus, special relativity informs us that time is not uniform for everything and everywhere. It is contingent upon how entities are moving. This notion challenges our typical perceptions of time and space. It's akin to stating that our ordinary understanding of the cosmos may be slightly skewed. According to the special theory of relativity, time is not static. It is affected by motion. Certain fundamental concepts, such as the speed of light remaining constant and the interrelation of energy and mass, have been confirmed by countless experiments. But there's more. Enter Albert Einstein's general theory of relativity from 1915. This theory delves deeply into the connection between gravity and the structure of the universe. It disrupts the antiquated idea that gravity is merely a force pulling objects from afar. Instead, it indicates that gravity arises because space and time are warped or bent. It's akin to saying, hey, gravity isn't an enigmatic force. It's just how things naturally behave in the universe. According to Brian's interpretation, general relativity necessitates viewing the universe as a four-dimensional entity, merging three spatial dimensions with one of time. Within this framework, large entities like stars, planets, and even ourselves influence how space and time are molded around them. This shaping is what we perceive as gravity. Envision spacetime as a vast, flexible blanket. When a heavy object like Earth is placed on it, it creates an indentation. If you position something smaller, like a ball, near Earth, it will roll toward this depression. This mirrors how objects respond to gravity, not as a mysterious force, but as a reaction to the curvature of spacetime. General relativity offers a robust explanation for how celestial bodies navigate in our solar system, such as planets orbiting the Sun. It can precisely predict the trajectories of these planets, including how Earth follows an elliptical path around the Sun. According to Brian, this differs from the outdated concept of gravity merely pulling objects together, which struggled to elucidate how planets move as they do. The new idea is that space and time are curved like a flexible fabric, aligning more accurately with our observations. A crucial event that validated the accuracy of general relativity occurred during a solar eclipse in 1919. Sir Arthur Eddington led a team to observe how light from distant stars bent as it passed closely to the Sun. According to the theory, the Sun's mass would cause the starlight to curve slightly. During the eclipse, the observations corresponded with Einstein's predictions, affirming the theory's credibility. Just as motion can alter our experience of time, according to special relativity, gravity also influences time. In regions where gravity is exceptionally strong, time progresses more slowly compared to areas with weaker gravity. So, if you were situated near a massive object like a black hole, your clock would tick more slowly than one placed far from this immense mass. General relativity presents the idea of black holes, which are regions where gravitational forces are exceptionally strong. Within a black hole, the gravitational attraction is so immense that nothing, not even light, can break free. The perimeter around a black hole is known as the event horizon, serving as a point of no return. Once an object crosses this boundary, it is pulled into the black hole with no possibility of escape. Einstein's general theory of relativity has significant consequences for the configuration of the cosmos. Initially, he integrated a concept called a cosmological constant into his equations, as he thought the universe was unchanging. However, upon discovering its expansion, he considered this a major mistake. The idea of an expanding universe, based on general relativity, is a vital element of the Big Bang theory, which outlines the origin of the universe. Another important idea stemming from general relativity is gravitational waves. These are disturbances in the structure of space and time caused by extremely massive objects moving quickly, such as during the collision of black holes or neutron stars. In 2015, researchers at the Laser Interferometer Gravitational Wave Observatory, LIGO, directly identified gravitational waves, offering proof for another facet of Einstein's theory. Over time, scientists have conducted numerous experiments to verify the accuracy of general relativity, and consistently it has proven correct, whether by observing planetary movement, the bending of light, or the detection of gravitational waves. While claiming that gravity is a misconception might be startling, Especially since we encounter gravity every day, it is common in physics to explore and critique various theories. Researchers like Brian often challenge established concepts, and within the domain of gravity, some question traditional views of this fundamental force. One idea that opposes conventional gravity is known as modified Newtonian dynamics, MOND, which asserts that gravity behaves differently at lower speeds, particularly in galaxies, without the need for dark matter. Instead of introducing unseen matter, MOND proposes that gravity strengthens at reduced velocities. The discussion about gravity also includes the mysterious ideas of dark matter and dark energy, which were introduced to explain certain phenomena in the cosmos. Critics contend that these concepts are unnecessary and that alternative theories can adequately clarify our observations. Some scientists who disagree with Einstein's theory of gravity pursue new directions, such as theories involving unknown particles or forces that could alter or enhance our understanding of gravity. It is essential to emphasize that, in science, new ideas are not discarded. They are rigorously evaluated for their validity. For example, Einstein's notion of time. Within four-dimensional space, where time travel might be limited by the speed of light, has been creatively explored alongside ideas like wormholes and shortcuts. Stephen Hawking's chronology protection conjecture suggests that returning to the past seems improbable from a physical perspective. Ongoing experiments and observations aim to determine whether these new theories can explain phenomena like the force of gravity in ways that align with existing knowledge. While many theories have been proposed, none have convincingly replaced the well-established laws of gravity. Questioning and challenging established ideas are critical components of scientific progress, leading to further inquiry and a deeper understanding of the universe. In terms of gravitational theories, general relativity remains the most significant and effective one. Despite facing challenges and alternative theories, it consistently performs well in tests and accounts for various phenomena, such as planetary motion and the bending of light around massive bodies. General relativity persists because it is straightforward and encompasses a wide range of phenomena. As mentioned earlier, Einstein's special theory of relativity indicates that time can behave differently depending on one's motion. Now let's explore how this idea impacts real-world situations, particularly in space exploration. Space exploration is exhilarating yet challenging, as the cosmos is vast, and according to Einstein's theory, the speed of light is the highest rate at which anything can travel. This presents a substantial challenge for interstellar travel, even with advanced technology, due to the long duration required to reach the nearest stars. To understand what happens to time during space travel, consider the famous twin paradox. Picture this. One twin stays on Earth, while the other takes a swift journey to a distant star. Upon the return of the space-traveling twin, they find that less time has passed for them than for their sibling on Earth. This indicates that they have effectively journeyed into the future. Time is vital for space travelers, as the longer the expedition, the more time slows down. If astronauts were to visit nearby stars, where time significantly decelerates, they might age more slowly than individuals on Earth. While this may sound like a science fiction narrative, it is a genuine phenomenon resulting from the theory of relativity. Imagine if humans dispatched a crew to a star system not far away. Due to the extensive distance, the journey could last many years. Even if they travel rapidly, for the astronauts aboard the spacecraft, time would feel shorter due to the time dilation effect. While on Earth, a considerable amount of time would have passed. Time dilation affects not only living beings but also technology. Computers and communication devices on spacecraft must account for time dilation to ensure accuracy and effective operation. High-speed space travel poses physical challenges, such as prolonged isolation, exposure to cosmic radiation, and psychological effects from being away from Earth for an extended period. In our everyday lives, we can observe the implications of time dilation in the Global Positioning System, GPS. GPS relies on the precise timing of signals from moving satellites. As these satellites experience time dilation, it is crucial to factor in these effects for accurate GPS computation. Ignoring this would significantly undermine the precision of navigation systems. Now, let's explore why time moves in one direction. Time governs our lives in the universe, flowing from the past to the present and into the future. This one-way progression of time is fundamental to our existence. But why does time exhibit this unidirectional nature? To understand, we examine entropy, a concept that measures disorder or randomness within a system. Entropy, associated with the arrow of time, tends to increase over time, leading time to flow in one direction. The second law of thermodynamics articulates this relationship, stating that in any isolated system, total entropy will either rise or at best remain unchanged. In simple terms, entropy naturally escalates and does not decrease on its own. Observing how things become increasingly disordered around us helps illustrate the one-way flow of time. Imagine a deck of cards all neatly organized. If we shuffle them, they become chaotic and random. This shift from order to disorder exemplifies how time progresses in one direction, as demonstrated by everyday occurrences such as ice melting or a stirred cup of coffee becoming chaotic.